Okay, for those of you who are holding and joining with us here, today we're doing a webinar on flash steam. It's going to be by Kelly Paffel with Swedlock Energy Advisors. I see here that I'm just a couple minutes behind schedule here. I just getting myself connected electronic took more than I expected. I am Gary Moore. I'm with UE Systems Inc. and we're happy to have Kelly. Are you on with us, Kelly?
Yes, can you hear me?
Yeah, very good. Just a little bit of foundation here about UE Systems. We founded this company in 1973. We've got a pretty large global footprint around the world. We've got regional offices in the U.S. and Mexico, as well as one in Europe, one in Asia, one in Latin America. So we have quite a few direct employees out supporting our customer base, and we probably have something like 200 or so independent distributors worldwide. A little bit about Swedlock and Kelly. They offer engineering services. They do steam systems audits, project management, and they do a whole host of training programs. Some we do jointly with them on the steam trap examiner, where we go teach people how to test steam traps. And I think outside of that, Swedlock Energy Advisors does all kinds of different steam and energy-related services. If you have any questions during this webinar, there's a panel over on your right where you can type them in. If you raise your hand, I could unmute you. I'm not quite sure how that works on this system. I've had some trouble with it in the past. If I don't get to your question right away, Kelly or myself will get back to you after this webinar. So feel free to contact us with anything that you might want to know. With that, enough about us. Let's welcome Kelly Paffel with Swedlock. And what I'm going to do is, Kelly, I'm going to actually give you over the presentation to Kelly, and you're going to see here Kelly's computer.
Today, one of the things that I make comments when I'm talking and everything is flash steam. And the comment I will make to everyone today is we don't vent steam to atmosphere anymore. We can't afford it with the price of energy today. The thing is that you have to understand a little bit on flash. And the thing is that I kind of wanted to go through flash and say, great, we're going to have it. No matter in a steam system, we are going to have it, and how to deal with it. If you want, you can come to our website, www.swedlockenergy.com, and come to our best practice section and look at best practice number 26 and best practice number 27, which are the things I'm going to be discussing during this presentation. The thing is that when we talk about flash, why and when does it occur? And the thing is that, when we have steam systems, we want to have flash, then we know the system is working correctly. Other thing we have to understand, the effects of the steam system and condensate system when we have flash, and of course how to quantify and calculate. And then how do we recover? And if we don't recover, what is the energy loss? Flash occurs. If you look at item 1, that's 100 psi steam coming into the process. 100 psi steam, it's going to be 338 degrees. It releases the latent energy, condenses down into condensate. Condensate's also going to be 338 degrees Fahrenheit. So down at point 2, will be the condensate going to the steam trap, which is 338 degrees. As condensate passes through the orifice of the steam trap, it will see a lower pressure. And let's say if that is 0 psig, the condensate temperature has to come down to 212 degrees. How does it get its temperature of the liquid down to 212 degrees? Take a percentage of the liquid, change its state from the liquid to the vapor or flash steam. The thing is that for any given saturated steam or condensate pressure, there can only be specific values listed in the steam table. We call it the saturated steam tables. Release of each lower pressure condition, the heat energy that is released is called, the effect is called flash steam. Flash steam affects the condensate return line sizing, receiver tank vent sizing, steam system testing, steam trap discharge piping, energy loss, If loss increases chemical costs, if loss increases makeup water. And one of the things flash does, it causes water hammer if its condensate return systems are not properly piped. How do we come up with the quantity of flash? The simple equation has been around for years as SH minus SL divided by latent heat low times 100 equals the percentage of flash. The question is, what is SH? That's a sensible heat on the high pressure. What's SL? Sensible heat on the low pressure. What's LHL? Latent heat low pressure. Example would be a heat exchanger. We have a control valve that's supplying 100 psi to this heat exchanger. The process is absorbing the latent energy, condenses down into condensate, and the condensate in this condensate piping to the steam trap is 100 psi, or we said before 330 degrees Fahrenheit. Discharging into the condensate return line, which is at 0 psi, the temperature is going to be 212 degrees. If you go to the saturated steam tables, and if you look up the sensible energy of the liquid high, you will see it's at 308 BTU per pound. If you look at the sensible low, it's 180.33 BTU per pound. If you look at the latent heat low, which is LHL, it's 970 BTU per pound. If I put this into the equation, then SH equals 309, which is on the high side of the steam trap. To the discharge side of the steam trap is 180 BTU per pound. The latent heat's 970, so I divide that into this equation, which is 309 minus 180 times 100 divided by 970 equals 13.3%. Well, what does that mean? If there's 1,000 pounds of condensate flowing through this heat exchanger, 13.3% of the liquid will change state, or 133 pounds of condensate, or flash steam will form. The other thing you have to remember, if condensate's passing into an atmospheric system, the flash steam is going to expand somewhere around 1,600 times. Therefore, we have to make sure that we compensate the system, in the return system, for the amount of flash that's going to occur in a return system. Example, here is a process coming in. The steam's coming into this process, going through a control valve and being raised up to the condensate return line. This example, as we're going to show, is operating at 125 psi. The condensate line is operating at 0 psi-G. The flow rate is 12,000 pounds per hour. If I go through the calculations again, that the process consumption is 12,000 pounds, the process steam pressure is 125 psi-G, the steam load is modulating, the condensate return line pressure is 0. I go to the saturated steam table, I find SH equals 324 BTU per pound, SL equals 180 BTU per pound, LHL equals 970 BTU per pound. The percentage of the flash, 0.148. The amount of flash is going to occur, 1,760 pounds per hour. Now, if I do not recover that, the cost of steam, say it's $14.80 per 1,000 pounds of steam. If this loss goes on for 24/7 at 360 days a year, that loss is $227,000 if the flash steam is not going to be recovered. Therefore, these amounts, or dollar amounts, become very high very fast if we are not proactive with recovering flash. Example here. This is 2,800 pounds per hour. And let's say that the cost of steam is $10, and it's operating 24 hours a day times 360 days. This loss right here is $241,920. Unfortunately, we go by facilities all the time, and this venting is quite normal, unfortunately, and the losses are pretty substantial. Or we have these, no matter where I travel in the area, there's always somebody out there selling pails to cover up, collect the condensate that's dripping from leaks or flash steam like this example. But probably one of the things is it causes roof problems if we don't take care of the flash steam losses. The thing is that in modulating process applications, we have to deal with flash. So we'll talk a little bit more about that. So what are the other problems? Chemical, increased makeup water, damage to roof, ice problems, and safety. Oops, excuse me. Now the thing is that instead of going through all the equations, we have a simple table here, which is if you go down the left-hand side and let's say we pick up 200 psi, which is the initial pressure, which is 338 degrees, and if I vent that condensate to atmosphere, 18.7% of the liquid will change state from the liquid to the vapor. So this table is a nice reference if you do not want to go through the full equations. Talked about we got to have flash. Say, well, how do we recover the flash? You say it cost me $200 and some thousand. Great. How do I recover it? It's a great question. There are two types of systems in the steam systems. One of the systems is called non-modulating steam process, non-modulating. The other one is modulating. First one I want to talk about is non-modulating. The thing is, condensate and flash will be in two-phase flow, discharging from non-modulating systems. This type of a system, we can recover the flash in a flash steam system, or cascade, or a high-pressure condensate return system. Those are typically the two methods that are used. Okay, what do you mean by non-modulating? If you look at this slide and look to the right-hand side, you'll see an arrow pointed to the valve. That valve is not a control valve. That is an on-off valve. So when the process is operating, that valve is fully open, and the steam is not modulated to the process. In these cases, when we do this, that if you look down at the bottom of the print, where we show a steam trap, P1 and P2, we're always guaranteed a differential across the steam trap because the steam pressure is not modulating. Therefore, the condensate return line that's shown there can be at some pressure elevated, but it has to be lower than the supply pressure. The condensate can be sent back to the boiler plant under pressure. Here's another example. If you look at the upper right-hand corner of this slide, you will see another arrow pointed down. Again, this is a on-off valve. There's no modulation to the process. We have full line pressure going to the heat exchanger. Down at P3, P4, constant pressure differential across the drain device, be it a steam trap or control valve. And then with these devices that we can elevate the condensate up in the air. On the left-hand side, you see we elevate 10 feet. Just a rule of thumb, every foot rise is half a psi, but I have plenty of differential to work with because we're not modulating the steam. Flash steam from the condensate discharge can be directed into another low-pressure steam user. We call cascading. High-pressure condensate return system, a percentage of flash is greatly reduced by high-pressure condensate return line. The thing is that the higher the pressure in the return system, the lower amount of flash will occur. Therefore, in plants where we go to high-pressure return systems, we reduce the amount of flash. We elevate the sensible energy in the condensate. With this type of an operation, we typically do not go back to the deaerator, then we go back to a high-pressure receiver and be directed back into the boiler. Remember one thing, if you do not allow the condensate to be exposed to the atmosphere. You do not have to go through the deaeration process. Non-modulating flows, where can they be from? One great example is steam tracing systems. They do not modulate the steam to steam tracing. Drip leg steam traps, specifically like a high pressure 200 psi. We take that condensate and direct it back into a high pressure receiver or to the storage side of the deaerator. Another one is process uniheaters or uniheaters, process heaters, reboilers, corrugators, process heaters. All examples of steam flows that do not modulate that we can go back into a pressurized return system or a cascade system. The thing is, directing these flows back into a cascade system or a thermocompressor system, we must basically separate the condensate from the flash. That's why we put in flash tanks. Flash tanks have to be properly sized and installed. The thing is, where do I take that flash steam? I can take the flash steam to a heat exchanger to heat water, air, or any other liquid, or direct it into processes with the lower pressure steam requirement. The thing about the flash tank is the separation of condensate and flash. The other thing is we control the flashing process by the pressure in the flash tank. The other thing in the calculations of flash tank, you need to allow enough space for the flash to occur. And there are certain calculations that we go through to do that. The other thing is to reduce the velocity of flash steam to ensure no condensate carryover with the flash. We have to make sure that the flash does not carry any condensate with it or reduce the steam quality to the process. And this all comes into the calculation process. Tanks can be mounted vertically or horizontal. The most important dimension in the design of flash tank is the internal diameter. It's, again, large enough to ensure that the low discharge velocities of flash to minimize the condensate carryover, and there's enough surface area to release the flash from the condensate. One of the things that comes up quite a bit, if the condensate line is properly sized, then we'll get the separation of the flash from the condensate in the condensate return system. Unfortunately, most condensate lines are undersized instead of being properly or oversized. So therefore, we have to rely on the flash tank to do the separation of the condensate, the flash from the condensate inside the tank. The other thing that needs to be looked at is the outlet velocities of the flash tank. So make sure we're not exceeding 3,000 feet per minute. That means that we are dropping out the condensate from the flash. Again, I said a high percentage condensate industrial operations are not properly sized. Therefore, the flash tank has to provide the proper area for the condensate to release the flash steam. The common tank arrangements, what's shown in here, is the high pressure drains coming into the tank on the right-hand side, draining into the tank, separation occurs. Flash is coming out, going to a lower pressure steam system. And in certain applications, we're putting in safety relief valves because we are adding extra volume of steam into the lower pressure lines. Down below, on the low capacity systems, flash tank systems, we're putting a steam trap in for drainage. The higher capacities can be with a pump or a control valve. Here's a picture showing a flash tank. As you can see, it's a smaller tank with a steam trap piped off the side of it. The flash is exiting the top part of the tank. Here's a larger tank assembly. This is taking volumes in about 40,000 pounds per hour, and the flash is exiting at the top here. The condensate, as you can see on the lower left-hand corner of the slide, is being pumped back to the boiler plant. The other thing with question always comes up in comments from plants we don't have use for low pressure steam. What can we do? And the thing is that the low pressure systems is that we can thermal compress the steam. Therefore, we can take the low pressure steam and thermal compressor to a higher usable steam pressure. A lot of times I hear a comment, is this new? It's been in existence for 60, 70 years. Certain industries used it for many, many years. Other industries have not used it. The thing with the thermal compressor is basically a nozzle where high pressure steam is accelerated into a high velocity fluid. High velocity entrains the low pressure steam from the flash tank by momentum transfer, and then recompresses it into a divergent venturi. The result is an intermediate pressure that's useful to the plant operation. Example is in this print here. If we go back to the heat exchanger that I talked about previously that does not modulate, steam's coming in at P1, cross the valve, P2, we have no modulation, and we come down to P3 and P4 differential across the steam trap. Elevate the condensate up to P5, condensate is returned back to this tank that's operating at a lower pressure, somewhere below P1, so I have differential at P3 and P4. At the upper left-hand corner of the slide, you will see the thermal compressor. We have a motor steam, which is higher than our intermediate steam pressure. Now, the higher the motor steam, the smaller the venturi will become. But essentially, on the lower side of that thermal compressor, you will see the suction side. And basically, we're drawing the flash steam up into the thermal compressor, thermal compressing it, and then developing an intermediate steam pressure, thermal compressing. Use it in all types of industry. It's a great way to make a usable flash when I do not have the ability to use low pressure steam. The roadmap that we want to follow when we're doing this is define all non-modulating steam processes. Determine whether we can cascade it or thermal compress it or take the steam to a condenser type system but recover the flash steam. Remember, if I'm venting the steam to atmosphere, it's, $200, $300, could be $700,000 a year. Can't do that today. The other steam process I was talking about is modulating flows. Steam and condensate conditions will change and are not at a steady state. The modulating system has a modulating steam control valve to the process because the intent is to maintain temperature of the process. Maintain temperature of the process. Condensate discharge from the process must discharge into a vented condensate receiver. Process applications. The thing is the control valve is going to travel from anywhere from 0 to 100%. Really it's controlling pressure of the steam to the process to maintain a process set conditions. The steam trap or condensate control drain device does need differential. So as I come down to low pressures, I cannot afford to have back pressure onto those drain devices. The problem with this is flash steam recovery has to be done by external heat exchanger, or what we call a condenser. Example is on here. This is a modulating load. The modulating load, as you can see, P1, P2. The yellow arrow is showing the control valve. That control valve can modulate anywhere from 0 to 100%. If it modulates down to, say, 5%, then P3's pressure is going to change. If it opens to 50%, P3, which is the inlet to the steam trap down to the lower part of this slide, will change. The thing to remember that coming out of the steam trap, or P4, going to the condensate header, which is P5, P5 must be 0 PSI. To make this process work, P5 has to be 0 PSI. One of the problems we find in process applications is their pressure at P5, which puts pressure at P4, and we lose differential when the valve modulates down, which will back up condensate and cause water hammer. So remember, when you're putting a system in, P5 must equal 0 psi. Therefore, we bring the condensate into a tank, and these tanks have different names depending on the different industries that we go to. One of the industries calls them condensate tanks. Another industry calls them condensate hogs. Another industries call them flash tanks. There really are flash tank, condensate tank. We're doing the same thing as we're doing in the non-modulating loads, is allowing the condensate to be separated and the flash to be vented. No different than the flash tank, what we talked about. The outlet velocities have to be very low to make sure that we get no carryover condensate going out the vent. And we also have to make sure we have separation. We want condensate to drop to the bottom of the tank and be recovered or pumped back to the boiler plant. To recover this becomes a little bit more difficult, because the thing is that this tank pressure, as we're showing in this diagram here, has to be 0 psi. So if it's 0 psi, I cannot cascade it, and it's very difficult to thermocompress it. Therefore, to deal with it, I go into a condenser. The condenser is taking process fluids into this, basically a shell and tube heat exchanger, designed specifically for a condenser application. The flash steam is allowed to flow up into the condenser. The latent energy is absorbed by the process. Condensate is formed, and the condensate drains right back into the tank. End result that we're after is the flash steam is not vented to atmosphere. So at the top of this configuration, we would want to see no steam being vented to atmosphere. Now, condensate can be pumped, as is showing here, through variable speed drive pumps or control valve pump applications like this here, showing maintain level into the tank. But remember, the same philosophy in condensate tanks as we apply into flash tanks is the same calculations. We want separation. We want the flash to be separated and vented at very low velocities. I would say 95% of the vent condensers that we put in have less than a 6-month payback. I mean, venting flash steam is so costly to the plant today. The other thing that we apply, and specifically to areas that have ability to heat, the northern climates, we're heating quite a bit, is to put in an air heater, simply showing us this here. Basically, we allow the flash to come into this air heater, and we absorb the flash steam by heating up the air. Now, with these units, we've done process, air heaters too, where we've taken properly sized coils to condense down the flash and preheat up the air for the process. But I'll give you an example. I was at a facility last week. We were in a cool area. It was down into one production area, and the vent for the condensate tank system was right there. By just putting in a simple air heater, as shown in this print, we can collect that flash, or recover that flash energy, and provide heat for the building, which they said that the heating is on for about 185 days a year, which is a lot better than heating the outside air, which is no use to anyone. So this is just another way of accomplishing recovery of the flash steam. Very simple method.
Kelly, without interrupting you too much here, how much steam is vented? How much flash is vented to atmosphere? Just if you had to take a guess, if you walked into your average plant, would you expect to find it or not to?
Are they in North America? In North America? probably more than 80% of the plants are venting steam.
Wow, really?
It's quite
wow.
high. Yes.
All right, I'll let you continue. Sorry.
Yeah. If you go to other parts of the country, of the world, you know, it depends on the country and so on, that percentage drops dramatically. But anyway, the thing is that when you come into facilities, and the discussion I was having this morning is I need a heat sink, which is, what is a heat sink? Something I can take the energy of that flash going to atmosphere and absorb it. One is that domestic water, you know, for showers or things like that, depending on the campus setting. You know, you can use it for heating up water. Processed waters. You know, the discussions, I'll give you one example. In the paper industry, we heat up white water. Great heat sink. You need to heat tons of water up. So it becomes very viable to do it that way. Processed fluids, you know, any fluid that I have to heat up to some temperature, you know, 190 degrees, it's great. Thermal compressing. Some applications, it gets very difficult to thermocompress a very low pressure steam, say half a PSI. We have some applications where we've been able to do that. Very, very seldom, but it's there. The other thing is heating up air. You know, a lot of times we think condensers, we got to heat up a liquid. Think about heating air for a process, or even think about heating up air for building heating, comfort. Usually the condensers or condensate tanks are sitting in areas where people are, in the production areas where we can heat up air. So it's quite viable.
Kelly, can I interrupt you again? We have a question
Sure.
here. Somebody was asking us, Gary actually, other Gary, not me. Is there a flash tank or other heat collection device that you can attach to the vent line that is set for oxygen removal?
I didn't catch it. You want to repeat that?
They want to know if you can get a flash tank or a collection device that also will remove, on the DA, he's saying. I don't.
Oh, yeah. Great. You know, great question. Great question.
See, I didn't even understand the question. This is.
Yeah, I understand his question. That's great.
All right.
The only, and it's a great point. Thank you for bringing that up. The only place that we say it's acceptable for steam to be vented to the atmosphere is off the deaerator.
Well,
And
deaerator.
for people that,
Okay.
yeah, the aerator. You have to vent 1/10. If you don't know the volume, you have to vent 1/10 of 1% of the volume of the deaerator to atmosphere to make sure you're getting rid of non-condensable gases out of the deaeration process. Now, years ago, I mean, unfortunately, I go back a few years. I mean, maybe too many years. But there's designs of old deaerators that I walk into that already have the condenser in there. Somewhere along the line, we just forgot to do that. But for sure, it's a great application because we come off of there and we put in a condenser. And the thing about it is the heat sink is the makeup water going into the deaerator. So we pick up that BTUs and go into the deaerator. But yes, for sure. Even today, we don't even allow the vent off the deaerator to happen. But remember, with the condenser, it has to be properly sized so I don't create vacuum and keep the non-condensables inside the deaerator. I want to make sure that I am venting the non-condensable gases out of the deaerator. But
We got another one here, too. They're asking what's the minimum flash steam pressure required to use thermal compressing?
Wow. Depends on motive steam and things like that. 10
Not an easy
PSI.
answer.
Yeah, it's not an easy answer. It's really a lot of, balancing and everything else.
Gotcha.
I have done 1 PSI. It's very difficult. Even we've done work on half a PSI, which is also difficult. But it just depends on the system. It has to be designed for the system. So, great questions. Oh, excuse me. condensate tank design, again, the consideration of vent condensers to ensure that no significant pressure drop is created on a condensate receiver tank. So when we put the condenser on top of this tank, we can't really create any pressure. You know, the question comes up, well, if you don't have pressure, you're not going to have flow. That is a correct answer. So there is some pressure in that tank, but it has to be very low. The flash steam vent line from the tank to the condensing unit velocity should not exceed 900 feet per minute. The thing why we're very specific on that is the flash steam is going to be traveling in an upward flow, and we're condensing the condensate, and the condensate is going to be dropping down through that vapor flow, and we want it to drop. We don't want any velocity to keep the condensate going up into the condenser. It's a very important fact. A lot of times people forget about that. The thing is, the success of the installation is information. The more information you have, the more successful you have. You know, one of the things is that I understand the maximum flow rates. Everyone's, I need the maximum. And that's great, we need that. But the other thing is minimum flow rates. Unfortunately, most of the time we'll not get the maximum flow rate, but 100% of the time we get to the minimum flow rate. And if we don't take that into our calculations to understand that, it can create problems. Same thing with cooling flow rates. What's my max? So I have to design the unit for the max. But as critical as max, I need to know the minimum. The minimum flow rate I'm probably going to hit. The thing about it is that if I don't have enough cooling to be condensing down the flash steam, the last thing I want to do is pick up so much BTUs in the cooling fluid that I change state from liquid to vapor on the cooling side and create severe water hammer, or basically taking a condenser and creating a boiler out of it. So in applications where our flow rates for the heat sink or cooling could be questionable, we have to put in bypasses around the condenser to make sure that we do not create issues with the condenser. It's just part of the things that we have to look out for when we design the system. The other thing is, I talked about effects, and I can go into all the effects onto the system that flash, does cause us issues. One example is I take a steam line, 6,000 pounds per hour. The condensate line is also 6,000 pounds per hour. 1 pound of steam is 1 pound of condensate. I need to know the percentage of liquid and the percentage of vapor. If I go and look at the system specifically on liquid, it's going to be 1 inch. If I go and recalculate for a condensate line to be liquid and a vapor, it's 2.5 inches. You see the difference in the condensate line. And the thing about it is, one of the biggest issues that we go week after week after week at facilities is condensate lines are not properly sized. And that's a big, big factor. But therefore, remember, condensate lines are two-phase flow. Size them for liquid and flash steam. Here's your roadmap. Determine the modulating versus non-modulating, which I said before. Set a roadmap for recovering flash. Tell people it took years to get where you're at. It's going to take a couple of years to go and get back. But the thing about it for allocations, one of the things I was in a discussion this morning, the plant saying, I need a 2-year payback. Recovering flash usually has less than a 6-month payback. It's one of those items that has a great payback. And with that is my conclusion.
Thank you, Kelly. It's really very interesting. I guess I've known Kelly for an awful long time and been through more plants than I cared to met with him, but I didn't realize actually until you're going through this with me just how much energy is lost through this. I do have a question for you here from a guy who says, I'll see if I'm saying this right. He says, a platen in the steel plant's channels for steam flow. Okay, what he's saying here is this. I have a press, a heated press with steam, and since it's a cyclical, I compress air from the platen when the cycle starts and have air in my high-pressure receiver at the start of every heating cycle. how would you vent air from a system like this?
Well, the thing about it is that if I'm injecting air to push the condensate through the press, that's one thing. If I'm allowing steam air to come into the press, that's another answer. But let me say we're using air to push the condensate through the press and get it out of the press, so the next cycle will have steam into the press.
Mm-hmm.
The thing is that we come down, we do this, it's a separation just like a flash tank. Instead of flash steam, we take into calculations we're going to separate non-condensable gases.
So it's just air.
Just air. And we do the same type of a separation process, yes.
I got you. I've got another guy asking here, Sergio, actually, I believe he's out of Mexico. Could you repeat the consequences of sizing condensate lines incorrectly?
Sure. Let me go back here. The thing with undersized condensate lines, number one,
right,
water hammer. Okay, for people on this call, water hammers have pounding, shaking of condensate piping. One of the things you need to remember: 60% of component failures in steam systems is caused by water hammer. So 60% premature failures is caused by water hammer.
Really?
So undersizing condensate return line will cause water hammer.
And therefore failures.
Failures. The other thing is that if you undersize, you increase pressure in the return line, you lose differential across drain devices, be it steam traps, control valves, condensate control valves for drainage, but we back up condensate into the process. So we cause uneven heating of the process. And I can go on the list.
Yeah, I've got also hear from Doug Landers. He's asking, how do you calculate the cost of steam?
Great question. I mean, we should do a webinar on that.
Yeah.
If somebody wants to, if you want to email me, it's the reason why
I can do that. Yeah.
Email me your name. Reason I brought it up this morning. I've been working on a paper on how to calculate the cost of steam, and I'm almost ready to send it to print. But I'd be more than happy to share with you. It takes you step by step on it.
I got you. That'll be interesting to see because I know we have always talked about the burning of fuel to raise steam, but there's more to the cost than just that.
A lot more cost to it. I mean, the thing about cost of steam is that even bringing flash, if not recovering, is going to add to your cost of steam. Not bringing condensate back. I mean, it has a whole thing. And the thing about cost of steam, everybody that's on right now, you have steam systems. The one thing that you need to know before you do anything, what is the cost of steam? To go out there and justify flash recovery, the first thing you need to know, what is the cost of steam?
Well, you just lit up the question boards there. Everybody's looking for your paper on that. I've got another one here from a Jim Harvard and said, considering that some of the flash steam will heat up condensate and some will have to vent, even with the highly efficient condenser, what is typically the recovery rate in terms of percentage of BTUs recovered? I'm not sure that I said that.
Well, let me answer this. I understand what you're saying, and a couple points I'll make. Your benchmark today is 90% condensate return, 90%. If you do not steam inject for process applications, you have to bring 90% of the condensate back. That's your benchmark.
That's what you're trying to get to.
That's what you're trying to get to.
Gotcha.
The other comment, everything in the condensate return system, condensate tanks, condensate valves, every component, expansion joints, everything in that condensate return system today gets insulated. No condensate piping, valving, tank is not insulated today. Now,
is that a pretty fast payback recovery on insulating lines?
Sure. Find you an insulating contractor and get married to them. They're your best people. Because today,
Really?
Unlike it was 10 years ago, fuel costs are totally different than what it is today. And the other thing about fuel costs, it's not coming down. It's going back up.
Really?
Everybody knows that. So the thing is that insulating today is just going to continue to pay on and on and on. So.
Gotcha. Well, actually, with that, Kelly, can you see up there where you can change the computer back to me? Over on the right, you just change presenter or give the keyboard and mouse, I think. Or I can change it back to me. I'll take it from you here, Kelly.
I'm clicking, Gary.
I
want to thank everybody.
Well, okay. And you know what? Thank you, Kelly. It's always a pleasure. We've known Kelly for quite some time here at UE Systems. Kelly was the guy that first took me out into the field and taught me how to test steam traps, and I'm still trying to get my arms around that. But I think Kelly's been around steam his entire life. We do some steam trap examiner courses. Kelly's organization is the instructor on those. We've got one coming up here March 23rd and 24th in Ann Arbor. We're looking at adding a couple more here. We've got a couple sites on the table that we're trying to get ironed up. And if you go to swedgelock.com, they got all kinds of steam training opportunities for you as well. We have, of course, our other ultrasound level 1 courses, which have a section on steam and other energy conservation ideas as well as reliability. There's a few of the upcoming dates. Check back with us because we actually do add to those quite a bit. You can get details. We've got some steam trap information up at uesystems.com. You can get some details on electrical things and bearing monitoring, as well as other training courses. This webinar itself, we'll record it and put it back up there. If you got somebody else you think you might want to have listen to it, or you want to go back and catch one of the calculations, just come up to uesystems.com and you can just log in and see it again. We'll get another webinar coming up here soon, probably next month. I don't know what the topic is yet. I've got a few people in the pipeline. We'll see what we come up with, but it sure seems like energy conservation is a pretty hot topic. If you're trying to get a hold of Kelly or you want some information from there, that's www.swedgelockenergy.com. Kelly's got a ton of stuff up there that's very useful. Or contact us here at UE Systems, info at uesystems.com. I'm Gary M. at uesystems.com. You can get us toll-free at 800-223-1325 or call our local number. We didn't put our fax in there anymore. It's just everything's now email and telephone, so give us a ring. With that, I think we'll call it a day. I want to thank you again, Kelly.
Thank you.
Maybe we can get you back on for another one, maybe on the cost of steam, how you figure out your cost of steam.